All right, so today we're going to be talking about bivariate random variables. So we're moving from the one-dimensional random variables we've talked to up to this point to two-dimensional random variables, and after that we'll move up to multi-dimensional random variables. There are a couple ways we can think about bivariate random variables. One is if I have two univariate random variables. Let's say x is a random variable that goes to some sample space S to R, and y is some other random variable that goes from the same sample space to R. Then we call the pair x comma y a bivariate random variable. And one can talk about things. For example, we could say, what is the probability that x comma y is in some set A? Here, A would now be a subset of R2. And what we mean when we say x comma y is in a set A is if I have a picture of, say, R2. So here's R2. This is my x-axis. And this is my y-axis. If I have a set A here, what I mean is the probability of being an A is if I look at the inverse image into my sample space of all these points in A, that will give me some set which I can call, well, if I call the pair x comma y maybe z, I could call this set z inverse of A, where z is my pair x comma y. So mathematically it's well defined. Here z would be another name for my bivariate random variable, and it would go from S into R2. So we'll often write things like, often we'll write something like probability x is in A, comma, y is in B. Here, A and B would just be subsets of the real line. X and y are themselves univariate random variables. So just the normal random variables we've been talking to up to this point, univariate meaning one-dimensional. And we write something like probability x is in A, comma, y is in B. This comma here is read as and. And mathematically what this means is this is the probability of x inverse A intersect y inverse B. Typically, we don't have to work with this level of granularity, but it's good to know kind of precisely how to define these things mathematically. Practically, the way we work with bivariate random variables is we think about it kind of in this way, where it's a two-component vector where each of the components are themselves univariate random variables. So we can look at a kind of real simple example. So our example here is going to be a kind of twist on one that we've seen before. I'm going to look at a coin flip done 3 times, and I'm going to let x be either 0 if the last, that is the third flip, is a tails, and 1 if the last or third flip is a heads. And I could define a different random variable, say y, and actually y is just going to be simply the number of heads among the 3 flips. And so this is going to be if we look at, say, z here, z is my bivariate random variable, x comma y. It is what we call a discrete bivariate, or bivariate discrete random variable, because each of the components are discrete. the first component you take out either 0, 1, and the second will be 0, 1, 2, or 3. And we can represent z. Of course, it's a function, so z, recall, you can think of this z, or this bivariate thing, as a function. Now, before we'd say it from s to r, but now it's s to r2. And you could actually draw the table that says, for my outcome, little s in my sample space, what is, let's say, z of s, which is x of s, comma, y of s. Okay. Let's write that legibly. And so my different outcomes for 3 flips of a coin would be, well, let's write them all out. There are going to be 8 of them, and we can play a little game, a little pattern here to write them out systematically. Okay. Okay, so those are all the possible 8 outcomes. You can verify that. And my random variable is going to be now a 2-component vector. And x, if we recall, is the is 0 or 1, depending on the last flip. And y, the second component, is the number of heads. So y here is 3. We got 3 heads, and the last is a head, so that gives us a 1. The last is tails here, so we get 0. We have 2 heads. The last is a head, so the x component is 1. 2 heads, so the y component is 2. We'll have the last component is a tail, so we get a 0 on the first component. Number of heads is 1. Last is heads, so we get 1. Number of heads is 2. Last is a tail, so we get 0, and the number of heads is 1. Last is a head, so we get a 1. Number of heads is 1. And then we get 0, 0. Okay, so that's the table that defines our random variable. It tells us for each outcome, little s and s, what is the value of our random variable. But now, instead of the value just being a number, it's a 2-component vector. So we can find all these kind of similar, or analogs at least, properties of the things that we're used to dealing with in the univariate case. And so we're going to start, and we're going to define the bivariate version of a CDF, the bivariate cumulative distribution function. And this is going to be a function f, and now instead of going r to r, it's going to take in numbers in r2 and produce a number in r. And it's going to be defined for any pair xy in r2 as f of x comma y is the probability x is less than or equal to little x and y is less than or equal to little y. And the comma here, again, we can read this comma as and. So it's the probability that x is less than or equal to little x, y is less than or equal to little y. And so if I draw out a bivariate plane here, let's just draw out 2 axes, x and y. Well, let's leave them unlabeled. Here's our, just for clarity, here's our point x comma y. The probability, or the CDF, measures the probability of kind of being in this space. X is less than or equal to little x here, and y is less than or equal to little y. And so that defines this kind of partial plane here. And so it's the probability that we are in this region. You could, if you kind of knew the underlying probability function, you use inverse images. Typically, we don't do that. We'll get to how you can actually calculate this later in the lecture. But the bivariate CDF behaves in many ways like the univariate CDF. A real quick theorem is that it has kind of analogous properties as the univariate CDF. First of all, fx comma y is always positive. Better be because it's probability, as defined here. And in the univariate case, we had limiting properties at 0 and 1. In this case, now, the limit as both x and y go to infinity of fxy is equal to 1, right? If I keep pushing this point out that way, eventually I'm going to subsume basically the entire, or in the limit, I'm going to subsume the entire R2, and then the probability better be 1. And in the univariate case, it was just the limit x goes to infinity of f of x is 1. Third property is that if I look as x goes to negative infinity, that will give us 0. Or analogously, as y goes to negative infinity, fxy goes to 0. So in this case, it's a little more nuanced. If either of the arguments, x or y, go to 0, or go to negative infinity, then the whole thing goes to 0. Okay, and that's the analogous property as in the univariate case. If we send x to negative infinity, the CDF must go to 0. So it starts off at kind of 0, and if the limit of either of the arguments, if both of them go to 1, or both of them go to infinity, then we get 1. Better always be positive. A fourth property is f is non-decreasing. As before, better be an increasing function. And we can combine this with the other property is that it is right continuous, which was in direct analogy to the univariate case, and we can say right continuous in each argument. So in either x or y, it's right continuous. And so we looked at, among these properties, we looked at when both x and y go to infinity, or when x or y go to negative infinity. And so the question is, what happens in the case where one of them goes to infinity but the other one doesn't? So in order to understand the behavior there, we have to introduce what is called the marginal distributions. So this is another definition. So definition, marginal distributions. And this is basically just the distribution of each of the components, x and y, right? So if I have a bivariate random variable, xy is a bivariate random variable, then the distributions of x and y individually, if we just treat them as the kind of classic univariate random variables we've dealt with up to this point, these are called the marginal distributions of x and y, respectively. And we'll see later in the lecture why they're called marginal. But when we talk about marginal distributions, we're just talking about if we just were to ignore one of the components and just look at one of them, either x or y, they would have a distribution. If we just pull off one of the components, that's going to be a random variable. You got to convince yourself that's true. And so we can talk about the distribution of that, and that would be called the marginal distribution. Okay, so why am I introducing marginal distributions now? So it turns out that the theorem is that if I look at the limit as x goes to infinity of my bivariate CDF, fx comma y, this gives me the univariate CDF of y. So if I push x to infinity but fix y, this gives me the univariate marginal distribution, or we should say CDF of y. And analogously, so I'll say that's 1, we can say 0.2 is the analogous, is that if I send y to infinity and I fix x, this will give me what I'm going to call fx of x, and this is the marginal CDF of x. So that's a kind of interesting fact. The idea behind it is that the marginal, say, CDF of x, fx, little x, so we're going to denote that. This, remember, is the probability that x is less or equal to little x. And we could kind of write this as, this is the probability that x is less than or equal to little x, and, so comma, y is anything. We actually don't care. Let's just, a little kind of hand wave here, just write, this is that y is anything. So it's a probability x is less than a little x, and we actually don't care what y is. And another way to think about it is this is the probability that x is less than or equal to, little x, and y is just something. So we can say y is less than or equal to infinity, and that is exactly the limit as y goes to infinity of fx comma y. So that's kind of a little bit hand-wavy. That's pretty much the idea of the proof. And so it turns out if we take this marginal CDF and we run one of the parameters to infinity, we'll get, or sorry, if we take the joint CDF and we run one of the parameters to infinity, we're going to get the marginal CDF of the other one. And this here is a kind of cute little argument. You can think about why it's kind of equivalent to write probability that x is less than or equal to x is the same thing as x is little x and y is anything. Saying and y is anything is just kind of and the whole sample space. So it's kind of like intersecting with everything, or intersecting with the whole sample space. Not really going to change anything. And that can be made rigorous if you kind of think about the definition of probability of a bivariate random variable. If you go back and use the definition, the kind of inverse image definition. That's a bit cumbersome, but it can be shown kind of more rigorously that way. Okay. So if we have the joint CDF, we can get the marginal CDF. And the question then is, well, if I have the marginal CDF, can I get the joint CDF? Unfortunately, you don't have enough information to go the other way. So let's write that as an important note. Unless I tell you something else, knowing joint CDF will yield the marginals if I can compute those limits, but not the other way does not work. So other direction doesn't work unless I tell you some more information. We'll get to that later in the course, what kind of other information I would need to know to fully specify the joint given the marginals. But right now, the joint really tells us everything about the behavior of them. If I just know the marginals, I don't actually know all the behavior. I don't know how they interact with each other. I just know kind of marginally how they behave, and I don't know the interaction between them. And we'll get to that in a couple lectures when we start talking about independence of random variables. Okay. So let's look at some kind of other analogous lemmas to the univariate case that we have in the multivariate or bivariate case here. So here's a lemma. Lemma meaning just kind of short little fact. In the univariate case, I could say that if I wanted the probability that x was bigger than or equal to some little x, I could take 1 minus the CDF. In the multivariate or the bivariate case, if I want to calculate the probability x is bigger than little x and y is bigger than little y, I can take 1 minus the marginal CDF of x minus the marginal CDF of y and little y plus the joint at x and y. So it's a little more complicated formula, but we can calculate the probability that we're bigger than both little x and little y using this formula. If I know the joint CDF, I can get the marginals and I can calculate this. And this proof really lends itself to a picture. So let's draw my two axes here. And then let's specify a point, x comma y. And what I want to do, I'm going to draw some lines through this. What I really want is I want the probability of this. So this is the probability I want. let me actually write what this is. This is the probability. This area is a probability I'm both bigger than x, little x, and bigger than y. So this is the probability I want, right? I'm above this line y of little y, and I'm above this point of little x. So it's kind of this whole hashed region is what I want the probability of being in that area. What I could do is I could calculate the probability of being less than this little x. So if I look at this green area, this is the probability that x is less than or equal to little x, which is f, which is my marginal CDF of x. Why is that true? Because it's a probability that my random variable x is less than or equal to little x. It's all the area less than or equal to my x coordinate here. And I don't care about my y coordinate. The y coordinate can be anywhere. It's just the probability of, if I ignore the y and y can be anywhere, it's the probability that x is less than that. And kind of correspondingly, I could get this kind of red shaded region. This is the probability that, just looking at my y coordinate, the probability I'm less than or equal to little y, which is the marginal CDF of y. And so ignoring x is just kind of the probability I'm less than or equal to this value y here. And so if I want to get kind of the area or the probability of the black shaded region here, I know the kind of total area of the whole thing should be 1. I can subtract off the probability of the green, subtract off the probability of the red. Unfortunately, then I've double counted, let's do this in blue, I've double counted this region here, this kind of square here, and that square is, as we said above, is the joint CDF. It's the probability I'm both less than little x and less than little y. And so I double counted that, and so I have to add it back in. So I take 1, which is the total probability, subtract off probability of that one section, subtract off probability of the other section. Whoops, I've double counted, and add back the joint. Add back the probability, that kind of blue square here. And there are extensions to this formula. An extension to this is I could look at, say, what if I want the probability that x is between little x1 and little x2, and y is between little y1 and little y2. And the extension formula is a bit nasty. It's the joint at x2, y2 plus the joint at x1, y1 minus the joint at x1, y2 minus the joint at x2, y1. And I'll let you think about, we can do this with a similar picture proof. And you can think about how to convince yourself that this formula is true, but it's going to look just like this picture proof up here, but it's just going to have a bunch more regions in it you have to keep track of and kind of add and subtract them. But it's a similar kind of formula. And if you send off, notice you send off, say, if you send off x1 or y1 to infinity, you're going to just get the previous theorem. And, oops, this should be a y2 or x2. And you'll get that because of this theorem up here. If I were to send off either x or y of the joint CDF, I'll get the marginals. And so you can imagine if I send off certain ones of these certain terms in this formula will reduce to the marginals, and it will give me exactly the formula of the kind of more basic lemma here. So that's kind of exercises for home that you can think about how to do. What's more interesting to work with, certainly in the univariate case, and it's going to be similarly important in the bivariate case, is the PMFs and PDF. So let's look at how we can extend the definitions of joint PMFs and PDFs to the bivariate case. And so we're going to define first what is called a joint PMF. And so this is going to be in the case where if x and y, that's not well written, if x and y are discrete, then we're going to have our bivariate random variable, xy, is kind of bivariately discrete. We define the joint probability mass function, PMF. Now it's a bivariate function. It's f of xy instead of just f of x. And it's going to be the probability that x is equal to little x and y is equal to little y, right? Remember, in the univariate case, the joint PMF is just a probability that x is equal to little x. Now we have a bivariate PMF, and this probably x is equal to little x and y is equal to little y. And it will have all the same properties, or some very similar properties. So I'll just write these as facts. I'm not going to prove them, but they're not too hard to verify. Is that if I sum my joint PMF, xy, over all possible values of x and y, so when I'm writing this sum over x and y, I'm not really specifying. I mean just sum over the whole support of both x and y. If I sum up everything, I get 1. The probability of something happening is 1. And if I, and similarly, the probabilities always have to be positive, so this function always has to be positive. This is fx. X comma y has to be positive. And this is just exactly analogous to the univariate case. And I'm not going to go through and prove those, but so the joint PMF is just, okay, well, now we're going to have multiple components. The interesting facts come in when we try to relate the joint PMF here to the PMFs we're used to of each of x and y individually, what we call the marginal PMFs. So let's write this as a theorem. So this is joint / marginal marginal PMF relationship. And the theorem says that if I want, and we're going to write fxx, which is this is the marginal PMF of x. So if we just treat x by itself, forget about y, it'd be a univariate random variable, it'd be a discrete random variable, have a PMF. We call that fx of x, and that is related to the joint if we sum the joint PMF over all possible values y, and we're going to write it like this in the support of y. So we sum over all possible values of y, the joint, fixing x. That will give us the marginal for x. And similarly, so like that as a 1, 2, if I want the marginal of y, what I can do is I can sum over all possible values of x. I'm just going to write over x of the joint. So what I do is if I want the marginal at some of y at some value little y, I fix that little y and I sum the joint over all possible values of x with that fixed value of y plugged into my joint PMF. We can do a kind of short little proof of this. So here's the kind of a little bit hand-wavy proof. But if I want the marginal of x, right, this is the probability that x is equal to little x. And I could say this is the probability that x is equal to little x and y is equal to anything. I don't actually care about what the value of y is, so I can kind of think about it that way. It's like intersecting with the whole sample space. It doesn't change anything. It's not going to change the probability, say, if I fix a particular value for y, then my probability might change. But if I just say x is equal to x and y is anything, it's not going to affect my value of x. And so it's kind of equivalent. And I could write this as summing using kind of a, or exactly using the additivity property of probability functions, I could just say, well, I could break it out to be saying, well, it's probably x is equal to little x, and y is equal to 1, y is equal to 2, is y is equal to 3, you know, and I could sum over all the possible values of y, and that is precisely just as we defined fxy. Probably x is equal to little x and y is equal to little y is our joint PMF. So that's the proof of why that's true. And so let's look at an example, which is going to be much more illustrative here. So the example is, we're going to continue our example. So continue coin flip example. And so we flip a coin 3 times, and x is equal to 0, 1 if 0 if third is a tails, 1 if third flip is a heads, and y is just the total number of heads. So for discrete bivariate distributions, we can always visualize these as a table of values. So here's my table of values. Okay, so I'm going to have x here, and I'm going to have y here. Now x can take on 2 possible values, 0 or 1, and y can take on, 4 possible values, 0, 1, 2, or 3. So it could be 0, it could be 1, it could be 2, or it could be 3. So here are all my possible values. Okay. Draw a little table like this, extend these lines, and we could now get, so in each of these boxes I'm going to put, say, f of x, y. I'm going to put the value of my joint PMF. I'm going to say the probability that we get this pair x and y. Okay, so what's the probability we get x is equal to 0 and y is equal to 0? So that would be this box here, right? The probability that x is equal to 0 is that the third is a tails, and that the number of heads is 0. So the number of heads being 0 means we flip 3 tails, so tails, tails, tails. That will occur 1/8. If we go down to the next box to say what's the this one here, and we say what's the probability that y is 0, that is we get all tails, and x is 1, that is the third is a head. Well, 0 probability. We can't have 3 tails, but the third one be a head. So 0 probability. We can continue on. Let's say what's the probability that y is 1, so one of the flips is a heads, and that the third is a tails. Well, that could be 2 of the 8 possibilities. So that will give us 2/8, right? If one head, it could either be head, tails, tails, or tails, heads, tails. But it can't be tails, tails, heads, because we know the third is a tails. So there are 2 out of the possible 8 flips there. And we could go down to this box here and say what's the probability that y is 1. So one of them is a heads, and the last is a heads. Well, there's only one possibility. The last one is a heads. That's 1 of the 8 possibilities. Continue on. Total number of heads is 2. So if we're looking at this box, total number of heads is 2, y is 2, and the third is a 0. Third is a tail, so x is 0, third is a tails. So that must be heads, heads, tails. And so you can go actually and look back up at your table. That would be a real good way of looking at this. So that'd be heads, heads, tails. So that would be 1 of my 8 possibilities. Okay, let's look at this box. 2 of them are heads, and the third is a heads. So that could be tails, heads, heads, or heads, tails, heads. So 2 out of 8 possibilities. In this box, we have y is 3, so we get 3 heads, and the third one is tails. Not possible. 0 probability. You can't have the third one be heads. our third one would be a tails, but have 3 heads. And the last box here, finally, we get 3, y is 3 again. So we get 3 heads, and the last one's a heads. Well, that can happen, heads, heads, heads. So that is 1/8. Okay, so this is our joint PMF. It gives me, and kind of for each of our possible values, combination of x and y, x being 0, 1, y being 0, 1, 2, or 3, gives me the probability. Now, I claim in my theorem, or a fact, is that, first of all, so my 2 facts true. One is that they better all be bigger than 0. The table is full of f, x, y. Yeah, they're all bigger than 0. Do they sum to 1? If I sum over all values of x and all values of y, they sum to 1. Hopefully. 1/8, 2/8 is 3/8, 4/8, 5/8, 7/8, 8/8. Okay, so they all. So if we sum over all possible values of this thing, so we check. Let's say we check that fxy, which this table is they're all bigger than 0, and so that's 1 and 2. If I sum over all possible values of x and y, and I sum up fxy, that gives me 1. Cool. Okay, so let's now get the marginal distributions of x and y. We kind of know what they should be, I think with a little bit of intuition, but we can derive them from the joint using this theorem here. So we can, if I want to get the joint of x, I fix x and I sum over all the values of y. If I want to get the marginal of y, I fix y and sum over the values of x. So in the table, we call it marginal because we're going to write these in the margins of this table. This being one margin, this being another margin. So this is where the name marginal distribution comes from. And so let's write. So if I want fx of 0, what I do is I fix x at 0 and I sum over all the values of y. So I sum those up. If I sum those up, that's 1/8, 3/8, 4/8, so that's 1/2. And if I want fx of 1, I fix x at 1, I sum over all the values of y. I'm going to put that over here. That will also give me 4/8 or 1/2, which we kind of know has to be the answer, right? If x is just 0, 1, if it's the third as a heads, it's a 1, 0 if it's tails, right? 50-50, that should happen. So this is my marginal distribution of x. This is fx of 0, and this is fx of 1. Only 2 values for x, so that's the entire marginal distribution. And if I want now the marginal for y, so I'm going to write them in these spots here, right? So I'm going to say fy of 0, that corresponds to this, fy of 1, fy of 2, fy of 3. What I do is I fix y, say fix y at 0, and I sum over this. That gives me 1/8, so fy of 0 is 1/8. Fy of 1 will give me 3/8, because I'm summing over that column. Fy of 2, I'm going to write here, fix y at 2, sum over this column, 3/8, that works. And fy of 3, fix y at 3, sum over all possible values of x, 0 and 1, and that gives me 1/8. So this is my marginal distribution of y. It goes 1/8 at 0, 3/8 at 1, 3/8 at 2, 1/8 at 3. Okay, so that's a nice little example in a short little discrete problem of how I can get my marginal distributions, or how my marginal are related to the joint distribution. And that really comes about from, the word marginal comes from, typically people write them in the margin of the table like this. But I can get the marginal from the joint by just fixing the value, and then summing over the other variable. Okay. So let's continue on. So we talked about discrete. Presumably we can do something similar in the continuous case. And indeed we can. We're going to define something that we call the joint. So let's call this definition. Joint, instead of PMF, now it is a PDF. So this is for the continuous case. So if x and y are continuous, then x comma y is kind of a bivariate continuous random variable. And we call the function f, which is going to be a function that takes in two numbers, x and y, and gives me out a single number, so r2 to r, we call the function f the joint PDF of x and y if for all subsets A of R2, if we want to calculate the probability that our joint random variable x comma y is in this subset of R2, all we need to do is we take this joint PDF and we integrate it over A. Now it's a double integral. I'm just going to write it as one integral over A, but it's a double integral with respect to both x and y, right? So x and y are continuous, okay? This is not a super useful way of defining it, but it is the correct mathematical way to define it. We'll get to the useful properties. But basically, it's the function. This is a very useful relationship. It says that my joint PDF, what it's going to allow me to do is say if I want to get the probability that my joint, my x comma y, is in some subset of the plane, R2, all I have to do is integrate that joint PDF over that set in A. And I integrate now with respect to x and y, and this is exactly what we had in the univariate case, except we just had f of x, and we integrated with respect to x, and it was A was a subset of just the real line, but now everything's just two-dimensional. So it's actually, I think, pretty straightforwardly analogous to the univariate case. So some facts about this that hopefully won't be too surprising. They're really kind of analogous to the univariate case. Facts about this. My joint CDF, f of x comma y, we define this as a probability that x is less than or equal to x and y is less than or equal to y. And so we could write this in terms of the joint PDF now. All we need to do is integrate over the space defined by x being less than little x and y being less than little y. And so if I integrate with respect to x first, I integrate from negative infinity to x and negative infinity to y. And this is super analogous. I'll just say, recall in univariate case, we had the fact that my univariate CDF for x was the integral from negative infinity to x, f of x dx. And now it's a similar kind of thing, but now we just have two variables. So I have to do another integral with respect to y from negative infinity to y. And the picture here is if I have some little x, little y, my joint CDF kind of gives me the probability of being in this square here. And so what I do is I integrate, let's see if I can write this legibly, if I have my density function, my joint probability density function, joint PDF, I can just, if I want to get the probability in that area, I can just integrate this joint PDF over that area. And the bounds defining that are negative infinity to x and negative infinity to little y. And I integrate my joint PDF now in this case, right? So the joint PDF plays the same role as the univariate PDF. It tells me the density of probability at each of the points, but now it's each of the points in a plane instead of just each of the points on a line. Okay, the other facts here, so this is kind of fact one. The other fact here is that in the univariate case, I had this relationship that my PDF I could get by just differentiating my CDF. And we have a very similar relationship in the bivariate case. If I want to get my joint PDF, all I have to do is I take my joint CDF, and now I'm going to take derivatives, but now I have to deal with the fact that I have to take two derivatives, one with partial derivative with respect to x and one partial derivative with respect to y. Doesn't matter the order I do it in. So now it's kind of the second mixed partial derivative. And so that's a very useful fact. We'll see some examples of that. And you get that just by taking this relationship up here and taking derivatives. If I take derivatives, I can basically cancel out these integrals. And so if I take derivative with respect to y, cancel the first integral, take derivative with respect to x, I'll cancel out the second integral. And so that mixed partial derivative will just leave me with fxy left over. So I'm not going to go through the whole proof of it, but that's basically the case. And the third property, which is kind of a two-parter here, is, so other, let's say, other similar properties. Properties similar not only to the univariate case, but to the bivariate PDF, is that one, my bivariate, similar to bivariate PMF, my bivariate PDF is also always bigger than 0, and my bivariate, if I integrate, take a double integral of my bivariate PDF, and I integrate over the whole real line for both coordinates, I'm going to get 1. So this is similar to what we had up above. If we go back up here and we look at the sum, where did we say this? So this is our facts about the bivariate PMF, was they're bigger than 0. If I sum over all the values, I get 1. Well, now it's bigger than 0, and if I integrate over all possible values, I get 1. All right? And this is even more analogous to the univariate case. So in our univariate case, we said that my PDF was just always bigger than 0, and if I integrated my PDF over all possible values, I would get 1. So in the same way, all of these properties are kind of going to be true, and I'm not going to belabor them because they're really similar to the univariate case. So what other properties have we talked about? So the other property we talked about for the bivariate PMF, so we had this example, right? And what we're doing, we had this theorem that related the joint PMF to the marginals here. So there's going to be a similar theorem for the joint PDF in relation to the marginal PDFs for the continuous case. So, right, so remember in our case, we have x, we have a y, they're both continuous, so jointly they're continuous. We can define a bivariate PDF, but they also have marginal PDFs in this case, so just x and y individually. And so the theorem in this case is that, let's write this down as a theorem. The theorem here is that if I want to get the marginal PDF of x, so here is the marginal PDF of x, so I'm writing f subscript x, say it's the marginal of x, at little x, what I'm going to do in the discrete case, I summed over all the values of y. Now I'm going to take my bivariate PDF and I'm going to integrate over all possible values of y. And so I'll just write integral with respect to y over all r, but really you can think about it over the support of whatever y is. So that's kind of part 1. And part 2 is similarly, if I want to get the marginal of y, what I can do is I'll take my joint, I'll fix it at y, and I integrate out all values of x. So in the univariate case, we kind of would sum over the table, the columns or rows of that table. In this case, let's just look at the first one. If this is my xy axis, and I want to get the marginal PDF, so this is x, I want to get the marginal PDF of x at this value, little x, what I kind of do is I I look at this line here over all possible values, and I integrate my joint fxy, my joint PDF fxy over this line. So it's kind of like summing over the column of a table. And in the similar case, if I wanted the marginal of y at some value little y, instead of summing over, say, the row of the table, I'm doing kind of the continuous version where I look at all possible values of x. So I go all over the possible values of my x, and so I integrate this joint PDF fxy over this line. So that's kind of the analogous to summing over the column or the row of the table now, but that one a continuous case. Okay, but that is a very similar relationship between the joint and the marginal. So if I want the marginal, I integrate, what we say is we integrate out y. If I want the marginal of x, I integrate out y. If I want the marginal of y, I integrate out x. So I integrate over all possible values of x, keeping y fixed, and I just integrate all those values of x. So let's look at an example of this. This is kind of our analogous to the kind of table of the 3 coin flips above, but now in the continuous case. So let's look at an example. Let's actually start first by specifying the CDF. So here I'm going to give a CDF. So this is a joint CDF for a continuous random variable. And I'm going to write it like this. It's 0 if x is less than or equal to 0, or y is less than 0. It's the product xy if x and y are both in the unit interval. So both x and y are in 0 to 1. It's x if y is bigger than 1, but x is in the unit interval. It's y if x is bigger than 1, but y is in this unit interval. And it is 1 if x and y are both, bigger than 1. Okay, it's a very abstract function. Let's draw the picture associated with it. So here's my picture. And so x-axis, y-axis, here's 0, 1 on the x. Here's 0, 1 on the y. I'm going to draw the boundaries of this unit interval, which shows up a lot in this joint CDF. And let's write down the values for this joint CDF here in green. So let's say this is in green. It's 0 if x is less than or equal to 0, or y is less than or equal to 0. So it's kind of 0 all the way out here. If either x or y are less than 0, it's all 0. If x and y are both in the unit interval, it's xy. So its value is xy here. If y is bigger than 1, so we're kind of above this line, but x is in this unit interval, so x is kind of left of this green line, it is x. And alternatively, it's y here, where x is bigger than 1, but y is between 0 and 1, and it's 1 out here. Okay, so that's the joint CDF. We can get the joint PDF. So the first question is, joint PDF? Well, how do we get the joint PDF? We know that fxy is ddx, ddy, the partial with respect to x and y of my joint, and I can do those partials in either order I want. So that if I want the joint PDF, I can take the partial with respect to x, and then partial with respect to y of the joint CDF, or reverse, partial with respect to y, then partial with respect to x. And so let's write the values here in red. So red, let's say red equals joint PDF. And so all I need to do is take the values in each of these kind of boxes and differentiate them. Well, 0, derivative of 0 is 0, derivative of 0 is 0. So all these zeros stay 0. If I take a constant and take any derivatives of it, I'll get 0. So in kind of this area out here, that's 0. In the region where the joint CDF is y, if I take the derivative with respect to y first, I'll get 1. Take the derivative with respect to x, I'll get 0. And similarly over here, where it's just x, if I take the derivative with respect to x first I get 1, then I take derivative with respect to y, I get 0. The only interesting place is in this region, in the unit interval here, or unit square here. If I take the derivative, the CDF is xy. If I take the derivative with respect to x first, I'll get y, and then y I get 1. So the joint PDF is just 1 in that region. So the joint PDF is actually pretty easy. It's just 1 if x and y are in this interval 0 to 1. They're both in the interval, and it's 0 everywhere else. So this is basically a uniform distribution over, now instead of an interval, it's over the unit square here. It's 0 everywhere in red here, and it's 1 in this square. And so it's basically joint. So this is basically a bivariate uniform over the unit square, 0 to 1 square. And you might guess is that the marginals of bivariate uniform, if I'm just as likely to be anywhere in the square, actually the marginals are going to be uniform over 0 to 1. But we can actually show that formally. Our intuition is that, okay, if I just look at the marginals, they should just give me the uniform distributions also. And we can show that formally. So let's look at kind of how to show that formally. We have our formula, which says if I want to get the marginal of x, so let's just say marginals. Marginals? What are the marginals? I want the marginal of x. I integrate over y over all possible values. And we know that the only places where this thing is positive is actually in the unit interval. So it's actually, I'm just going to have to integrate 0 to 1. And fxy dy, of course, fxy is just the value 1 in this interval. So you have 0 to 1 of 1 dy, and not too surprising, it gives me 1. So this is true for x in my unit interval. If x is outside the unit interval, I'm just going to get 0 because this fxy is going to be 0 everywhere. And so x is uniformly distributed over 0 and 1. So the marginal distribution of x is a uniform. Bivariately, kind of x and y are uniform over the interval. But x and x has a marginal of a uniform. And we can say that this is going to be true similarly for y. Not too surprising, we can do those calculations again. For y, we're just going to get that y is uniform. Y has the marginal distribution of y is uniform. That's how we would say it. Okay. So that's a kind of starter beginner example. Let's look at some more interesting examples. So let's do a kind of similar example here. We start with the CDF. We go from the CDF, we get the PDF, and then we can get the marginals. And so let's look at what's going on here. Okay. So example. So I'm just going to draw the picture for the CDF. Okay. So we're still going to be kind of focused on this unit square from 0 to 1. So 0 to 1. And I'm going to draw some boundaries here, just like I did before. So I'm going to write CDF, the joint CDF, in black. And I'm going to say that my CDF is going to be 0 in all these values here. Let's not write it in black. Let's write it in something different. Let's write it in red. So fxy is going to be in red. And so we're going to hit 0 everywhere where x or y is less than 0. And we're going to draw a line where x is equal to y. That's supposed to be a straight line. X is equal to y. Okay. And let's see, what do we want this to be? We're going to say that the CDF in red here is 1 in this kind of region. X and Y are both bigger than 1, it's 1. If Y is bigger than 1 and X is between 0 and 1 in this kind of region here, we're going to say it's X minus X log X. Okay, I'm allowed to do that. In this triangle here, I'm going to say it's X minus X log X over Y. And over in this remainder region, which is this whole kind of trapezoid, I'm going to say it's Y. Okay. So that's the CDF. You could write it out in a piecewise form, but it's probably not worth it. That's the CDF. So what about the PDF? Let's look at the PDF in green. fxy is green. And recall that I can get the PDF at each of these points, the joint PDF, by saying fxy is if I take the mixed partial derivatives, dx dy, of my joint CDF. Okay, well, places 0, it goes to 0. That's easy. Derivative with respect to 0, 0. And at 1, it's just a constant. It goes to 0. In this whole trapezoid here, where it's just y, if I take derivative with respect to y, it gives me 1. Take derivative with respect to x, that gives me 0. So that goes to 0. And up where it's x minus x log x, take the derivative with respect to y first. That will give me 0, right? Just a constant with respect to y, so that's 0. The only interesting place where anything is going on is this middle region here. So this middle region here is the region where we can write like this: 0 less than x less than y less than 1. So x and y are both between 0 and 1, and x is less than y. And the CDF, let's write it like this. Let's say for this region, the CDF we wrote as x minus x log x over y. You do have to verify that this is actually a legal CDF that satisfies all the properties I claim. It's a bit much, but one could do it. We can rewrite the CDF as x minus x log x plus x log y. Now that's just using properties of my logarithms. I can write the log of a difference as the difference of the logs. And I can now I'm going to take derivatives. It's easiest first if I say df d y. If I take the y derivative first, these terms involving just x will go to 0, because they're constant as far as y is concerned. And derivative with respect to y of log y is 1 over y, so I get x over y. And if I then look at the mixed partial with respect to x, that top will go away, and I'll just get 1 over y. So that tells me that the joint CDF is, or sorry, the joint PDF is 1 over y, 0 less than x, less than y, less than 1, and 0 otherwise, right? Now, the only place it's going to be non-zero is in this little interval, and it's going to have a value of 1 over y if it takes my mixed partial derivative correctly there. So the value of the joint PDF here is just 1 over y in this triangle. Okay, so this looks much different from the previous example. It is now not jointly, it is not just uniform over this square. It has a value of 1 over y over this triangle. It's much kind of different. But we can still get the marginal distributions in this case. So let's look at how we do that. If I want the marginals, so let's look at the marginal distributions. Fx, x, I integrate out y. So I integrate my joint PDF, and I integrate out y. And so I got to look at the boundaries. Well, let's just write R right now. But what are the boundaries that define how I want to do this. So my integral, I know my value is just 1 over y dy, and that's the joint PDF in this interval. But what is actually defining the boundaries of that interval, right? I'm taking derivative with respect to y. So if I look at my picture, pull back up here. If I look at my picture, if I fix a value of x here and then want the joint at this x, I got to integrate over kind of this region. Well, let's not block that out, but no good at this, am I? Okay, let's move this over here, right? So if I want the value of the marginal of x here, where x is somewhere between 0 and 1, I'm going to integrate kind of over this bar here. And that bar goes from, well, this line is defined by x is equal to y, so it goes from y to 1. And y is equal to x, so we could say it goes from x to 1. So if I want to get my marginal, I can integrate from x to 1 of my joint PDF. And what is this going to give me? It's going to give me log of y evaluated from x to 1, which is log of 1 minus log of x. Log of 1 is 0, and that's negative log of x. So that is my marginal distribution of x. Is negative log of x allowed for a marginal? Yes, because x has to be between 0 and 1. So this is, as long as x is in this interval. If it's outside the interval, it's 0. If it's inside this interval, it's negative log x. Negative log of x is negative in that interval, so negative negative gives me a positive number. Still satisfies all of my properties of the marginal PDFs that we learned. Okay, so we can also get the marginal of y. So that's marginal of x. Let's get the marginal of y. So I'm going to skip some of the formalism here. It's going to be similar, but now I'm integrating with respect to x. And now I'm just going to get the boundaries over which I integrate. So if y is between 0 and 1, so maybe y is a value here. I'm integrating kind of, that didn't draw straight, but presumably it's a straight line, right? I'm integrating this line here. And so this line here goes from, if that's my value of y, then the boundary starts over here at 0 and ends up over here at x. The x value is x is equal to y again, right? It ends on this line where x is equal to y. So the boundary of my integration now for this integral start off at 0, and I go to y. And so if I do this, it is going to give me, so now in this case, y is a constant with respect to x, so I've got to be a little careful. I can pull that out. It's just going to be a 1 over y. And my integral is just 0 to y dx. And so we get 1 over y. And I'm just going to get, what am I going to get? I'm going to get y, right? Gives me 1. So this is good as long as y is in my interval 0 to 1. So my PDF of y is 1 if I'm in this interval 0 outside. So y has a uniform 0, 1 distribution, right? The PDF of y looks like this. 0 to 1, it's 1 inside this interval and then drops down to 0 outside it. And that's classically the distribution, the uniform 0, 1 distribution. So marginally y is uniform. And x has some other kind of weird distribution. Okay. So that's kind of some nice examples of how we get the marginals from the joint and how we get the PDF or the joint PDF from the joint CDF. Now, let's look at some more fun examples of just calculating probabilities for this continuous case. So what do we want to look at? Let's look at this example. So I'm just going to give you, we're going to have a bivariate random variable distributed with a joint PDF fxy, which is 6xy squared for 0 less than x less than y less than 1. Oh, sorry, not quite. Just necessarily no relationship between x and y, just that they are both between 0 and 1. Okay, and by definition it's 0 everywhere else. So let's draw the picture. That's always the most useful way to do these problems. Draw the picture. 0, 1, 0, 1. So this is kind of the area in which I'm interested. And so my PDF is going to 0 outside this box, and it has the value of 6xy squared inside that box. And what I want to do is I want to calculate the probability that x plus y is bigger than or equal to, doesn't really matter for it's continuous, 1. Okay. Probability that x plus y is bigger than or equal to 1. That's my PDF, right? Now, recall that just like in the univariate case, if I want the probability that my bivariate is in some set A, all I have to do is integrate over that set A, the joint PDF. Now it's a double integral with respect to x and y, but I just have to figure out what the area, what the region A is, and then integrate my PDF over it. I've given you the PDF, so what remains is we got to figure out the area. So if we look at if x plus y is let's say equal to 1, this gives us a line of y is 1 minus x. So that would be this line here. This is y is equal to 1 minus x, or x is equal to 1 minus y, whichever way you want to think about it. That gives us that line. And if we want x plus y is bigger than this line, it's going to give us that shaded region. We don't need to go outside the bounds of 0 to 1 because our density is 0 there. So all we need to do now, this is just kind of a Calc 3 problem, is here's my area A, which I've drawn in green here. So let's say A. I need to integrate that. I need to integrate the function 6xy over A. And that's a Calc 3 problem. So I can write this and say the probability that x plus y bigger than or equal to 1 is the integral. So it's going to be some double integral of 6xy squared and integrate with respect to our two variables here, x and y. Okay, so all we need to do is figure out the bounds of this and then some calculus. So let's figure out the bounds here. The bounds for this, if I'm going to integrate with respect to x first, right? So I'm going to integrate over x first. I need to figure out kind of the relation of the bounds for y, right? So if I were to fix some value x, I would go from this point, and I would, oh, I'm sorry, we're going the other way, aren't we, right? So we fix some value of y, integrate with respect to x first. So we're gonna take slices like this, right? So I'm gonna fix my y value, and then we're gonna take a slice like that and integrate with respect to x. And if I do that, this value here is obviously 1 on that side. And if I know my value x at this point has to be equal to 1 minus y. And so I go from 1 minus y to 1. And then I'm going to do these slices like this. I'm just going to change my value of y between 0 here and 1 up here. So 0 to 1. So my boundary of y is 0 to 1. So at this point, it's just a Calc 3 problem. I'm not going to do all the calculus or kind of algebra basically at this point out for you. It should give you 90% as your probability when you do it out. but I'll leave that as an exercise to the reader, as it were. Okay, so that's it. So these kind of, you have probably a problem like this on some homework and maybe an exam. This could show up on the final. This is kind of a classic problem. I give you the PDF. I ask you to calculate the probability. It involves figuring out kind of the correct area, in this case this A, to integrate over, and then doing the Calc 3 problem to actually figure out what the integral of my PDF is over the area. We can look at another example here, and I'll set it up for you, and we'll talk about it, set it up, and then I'll let you solve it, and I'll give you the answer so you can check that you're doing it correctly here. So here is the example. So x, y are jointly continuous. They have a joint PDF of fxy is equal to e to the negative y, and this is good for 0 less than x less than y. Okay, so let's draw out the boundaries of this region. Here's my axes, xy. My condition of 0 less than x less than y. So here's the line, y is equal to x. Okay. And if x is less than y, we're going to kind of be in this shaded area here, right? So that's the region over which my PDF fxy is defined. It doesn't have to involve x and y, it's just e to the negative y in this case. But that's the region over which it's defined, and so it has a value of e to the negative y in this region. And 0 everywhere else, I guess it's defined. It's bounded by the y-axis here, because y better be bigger than 0. Okay, and we can ask the same problem. What's the probability that x plus y is bigger than or equal to 1? So I'll skip all the formalism. We need to figure out what the area is in this case. So again, if x plus y is equal to 1, this is the same thing as x is 1 minus y, or y is 1 minus x. So if we draw the picture, we have 1 here, we have 1 here. This is our line. It's supposed to intersect there. Y is 1 minus x. Oops, 1 minus x. And if we want x plus y bigger, then it would be kind of all the region over here. And so the region, the intersecting region where the PDF is bigger than 0 and our condition is satisfied is kind of this weird trapezoidal, maybe this weird shape here. So it's this blue region here. That's the region where the PDF is bigger than 0 and x is bigger than y, or x plus y is bigger than 1, according to our function here. So this is kind of A, this is our region A, and so to find the probability that x plus y is bigger than or equal to 1, I integrate my joint fxy dx dy over A, and it's kind of a Calc 3 problem at this point. My suggestion is what we're going to do is we're going to break this into two different problems. So we're going to break it into an A1, which is this region, and an A2, which is that region. So this would be a 2. And so you could equivalent write this. This is integral over A1 fxy dx dy plus the integral of A2 fxy dx dy. Okay, and we can think about how to set up these integrals. So let's just come down here. We'll set them up for you, and then we'll call it quits. So how do we set these up? Okay, so the first integral is going to be a double integral. Fxy we said is e to the negative y, and then plus something else. This is another double integral. Same function we're integrating, which is our PDF, e to the negative y. And now let's figure out in the first region, so this is A1, this is the integral defining the integral over A2. In our first region, if we integrate with respect to y first, then what we kind of do is we fix some value little x, and we're going to integrate kind of over slices that look like this. So, and that goes infinity up top, and it goes according to the line. Y will go from 1 minus x to infinity. So we integrate respect to dy, goes from 1 minus x to infinity, and then the value of x goes from 0 over here. So we then do all these slices like this over all the possible values here, right? And we integrate from 0 to the intersection point, which is not too hard to show. That's 1/2, right? That's the intersection of this line and this line. So 1/2. So we integrate with respect to x, 0 to 1/2. And we can play a similar game here. If the outer integral is with respect to x, it will go from 1/2 now to actually infinity. We can go as far up this way as we want. So 1/2 to infinity. And the integral with respect to dy, we're taking slices here. Now our slice here starts at y is equal to x and goes to infinity. And so we go from x to infinity. So you can solve these two integrals. What you should get out at the end of the day when you solve these, so dot, 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 some algebra in here is 2 e to the negative 1/2 minus e to the negative 1. So that's what I'm claiming the probability of that is. You can check my math there, that Calc 3 works out there. But it's just Calc 3 at that point. It's actually pretty much a Calc 3 problem after I've realized that the way to do this is just to integrate over that. Not necessarily easy, but it takes a bit of time. But it's stuff that we've seen before. Okay, so that kind of brings us up through the basics of bivariate random variables. We can just do a real quick recap here. Let's go way back up to the top. And so we first started off, we kind of defined what a bivariate random variable is. And the best way to think about it is just the components x and y are univariate, and we slam them together. And we can talk about now probability of x and y being in some region of R2 instead of just being in some part of the line here. And but ultimately, the way we define it is now our random variables mapped to things in R2 instead of just R. And you could define the bivariate CDF, which is the probability x is less than little x and y is less than little y. So kind of analogously, it has a bunch of analogous properties. And the marginal, so here's the kind of things to pay attention to. So our definition of marginal distribution is just the distribution of the random variables individually. And you can get that from the joint CDF either by taking the limits, which is usually not the most practical way. There's some other theorems about how to calculate probabilities. We can then define kind of similarly joint PMFs or joint PDFs, which is in the discrete case, joint PMFs is the probability x is at little x and y is at little y. And if we want to get the marginal PMFs, we just sum out the other variable. Either sum to get a marginal of x, we sum over y. To get the marginal of y, we sum over the values of x. And so we saw that with this coin flipping example. And you can define a kind of similar joint PDF, and has kind of all the same properties. If I want to get the joint PDF from the joint CDF, I take a mixed second partial. And if I want to get the marginals, now I integrate with respect to one variable the other, and that will give me a marginal. And then we looked at a bunch of examples, and I think it's good practice to go back through very carefully and work through these. I kind of gave you a couple where I set up the problem for you, and you can go back and fill in the Calc 3 details of how to calculate. Next time we're going to get into kind of defining expectation for bivariate random variables, and so we're going to continue on kind of generalizing all the concepts we've seen so far in kind of the bivariate case.